Hi and welcome to another edition of the Grasshopper Component Glossary. This is a tutorial about circles in Grasshopper. Please consider clicking the like button if you find this useful, and subscribe if you'd like to see more. That helps a lot. In this tutorial, we'll look at circles in relation to architecture and nature. This video will cover circle packing, a very useful way to divide up space for things like tiling and paneling. If you would like to download the Grasshopper script from this video, just head over to pavilion.nuluka.com. The link is in the description. Okay, let's get started. We're going to use this circle component in different ways. I just double-clicked on the canvas, typed circle, and I'm going to grab this orange one here. This component has two inputs, a plane and a radius. You can put just a point in this input, the plane, and it will assume the XY plane. That's what's right here, the XY plane. It has default inputs, one for the radius and the XY plane at the origin for the plane. So we already have a circle here on the XY plane, but if I type in YZ, we can get a circle that's flat on the YZ plane, or we can get any other plane that we want and put a circle onto that. And of course the radius controls how big the circle is, so I'll type in 0.000 to 20. We can't have a circle with zero radius, so nothing comes up, but as soon as I start increasing it, we get a bigger and bigger circle. So we're going to go through a few different ways to use this component, and we're going to cover a few different important features of circles in computational design and in biomimicry. Obviously, circles are very important. Circles are everywhere, so we could really talk about 1,000 different things regarding circles in nature, in design, in math. But for this quick tutorial, we'll focus mainly on circle packing. Dividing up a surface or dividing up space, three-dimensional or two-dimensional, is very important in design. It's very important in living organisms. It's very important in things like architecture. And there are a lot of different ways to do it and a lot of advantages associated with different packing or tiling methods if we're talking about surfaces specifically. Every living thing, all living systems, use different methods to their advantage of dividing space. It's just fundamental. And circle packing is a way to get the most efficient use of an area on a two-dimensional surface. And the circle itself encloses the greatest area for the smallest perimeter. So there's no other perimeter you can draw that has a higher ratio of area enclosed to perimeter. And when we pack circles on a surface, the flatter that surface is, and the more uniform in size the cells are, the more closely they resemble hexagons, like honeycomb. So anyway, we'll explore that a little bit, but first, I think I should at least mention sine and cosine, because we use these all the time in computational design too, and they relate, of course, to a circle. So sine is just the y-coordinate, and cosine is just the x-coordinate as we make our way around the circle. So as we make one full rotation around the circle, you can see that cosine, referring to the x, has gone from 1, this is x equals 1, all the way to -1, and then back up to 1. And sine, which is the y, started at 0, then went up to 1, down to -1, and then back to 0. So we use circles for a lot more than just their aesthetics. We use them for a lot more than their shape. They're fundamental to math too, of course. Anyway, let's move this and let's start our script. I'm going to hide all of this. So anyway, I mentioned earlier that dividing up a surface or dividing up any space is a fundamental problem for design, and it's a fundamental problem that nature has solved in a lot of different ways. You can think of scales on a reptile, bumps on a cactus, pores in different organisms, and then there are architectural analogs. There are so many different ways that we divide up space in design, and this problem of dividing up space gives us an opportunity to make some really interesting decisions. How do we do it, and what advantages come from doing it in different ways? So let's get a surface and experiment a little bit. I'm just going to get an empty curve, and let's reference one from Rhino. So I'll right-click here and say Set One Curve. Enter. Then I'm just going to internalize this, and let's delete the curve from Rhino. Now it's just in Grasshopper. Let's get a surface, and let's get a mesh, because we're going to be using Kangaroo in a little bit here, and we'll need a mesh. Also, I mentioned in passing just a little bit ago that if we have equally sized compartments arranged in the most efficient possible way, we get a hexagonal grid or a hexagonal pattern. So let's explore this on this surface by just doing a little physics simulation. Let's get our points. These are going to represent the compartments. These are going to be like the center of each compartment, or more accurately, they're going to define the boundaries around our compartment. But the problem we're going to solve first is how do we arrange these points on this surface so that they're all evenly spaced. Getting evenly spaced points on a surface is a really common problem in computational design, and it's something we see in patterns in nature all the time too. So let's make these points. I'm going to right click and say set multiple points, and let's put them all down here so that they're definitely not evenly distributed all around this surface. So I just put 63 points all kind of clustered over there. Then let's find what the average distance is between 2 points. So we're going to look at each point, see what the distance is to its nearest neighbor, then we're going to take an average of all those distances. So I'm going to get a graphed component, and then a distance component. Hide all these. Oh, we'll keep these for now. And then I'm going to get a list item component. And right now, the default here is 0. That means the first item in the list. These are all going to be 0 because it's measuring the distance to itself. Right now we have each branch is measuring the distance to each point. So the graph component put all these points in their own separate branches. And then we're taking the distance between those branches and all other points. So item 0 is going to be 0 because one of those points in that list is itself. But item 1 will be the next closest point. I'm going to flatten this list and get an average. So now we have the average between each point and its nearest neighbor. And we want to divide that by 2. So I'm going to get a division component and then // enter to get a panel. And let's just type 2 in this panel. So if we divide everything by 2, then we can imagine if we have circles there. Actually, let's do that. So let's get a circle component. And we're going to use these points as... I forgot one important step here. I'm glad I used the circle component. We need to sort the list first. Sorry, that might have been confusing. The lists, of course, are not automatically sorted. They're just according to whatever order the points are in this list. But if we use this component to sort the list, then we have all the distances from the smallest to the largest. And then if we pick the second item in those lists and average it, we get the average distance between each point and its closest neighbor. And then we divide it by 2. And so this is what all of the circles would look like. Some are overlapping because some are a little closer to their closest neighbor, and some are kind of out in the middle of nowhere. But if we were not to take the average, let's do this instead. Let's divide this number by 2. I'm going to copy this. Let's hide these. You can see that some of these are touching, like these two, their closest neighbors. Some, like this one, isn't touching anything because maybe this one's its closest neighbor over here, but this circle has a much smaller radius because this is its closest neighbor. So you kind of get the idea. Anyway, we're going to use the average of all of them just as kind of a guide to start us off. We're going to pretend that all of these circles have this radius, and they're going to push off of each other until they're at least that far apart. But then we're going to multiply this radius by a factor greater than 1. Let's go up to like 5. I don't know how big we'll have to go. But we're going to keep increasing the radius more and more. And so they'll push off more and more until they kind of arrange themselves all across the surface more uniformly. And to do this physics simulation, we're going to use Kangaroo. Kangaroo 2, which is part of Grasshopper. We don't need this circle anymore. So with Kangaroo, we need to collect a set of goals, a set of things that we want to happen, and then we're going to let Kangaroo take care of the physics for how those things actually happen. So one of the things that we want to happen is we want all of these points to stay on this surface, or mesh in this case. We turn it into a mesh so that we can put it into a Kangaroo physics solver. So the first thing I'm going to do is type show. One of the goals is actually to show these points. I'm going to copy this and hide this, put these up here. And these are our important points. we want to show them. And let's get an entwine. So I won't go into too much detail as to why we're putting it into a entwine component or what the show component does. What's important to understand here is that we have a bunch of physical goals that we're going to combine into this entwine, and then we're going to put them into a solver. We're going to use the zombie solver. So I'm going to disconnect this for now. So there are a number of different solvers in Kangaroo. There's a bouncy solver, a step solver, regular solver. We're using the zombie solver because it does everything internally and it just does it quickly. The other ones are good for things like animations, but we just want the result. And this is a very easy simulation that we're doing here. We only have two goals. We're going to put those in a merge component. Two goals besides this show. The first one, as I mentioned, is on mesh. So that's right up here under goals on mesh. It's this component. This is the mesh we want things to be on, and these are the things we want to be on that mesh. We want these points to stay on that mesh. I'll put that right here. The next thing we want is under this collider, goals co, or COL, it's collider one. Let's lift all these up a little bit. So these are the objects that are going to collide, and these are the radiuses that we just made over here. So let's pull all of this over, the radii. Let's just start at 1. And so another interesting thing you can do, we won't do in this tutorial, is you can vary the size of the circles essentially. And so you can spread these, you can have like bigger circles on this side and smaller circles on this side so that you have kind of a gradient of circles packed across the surface. But for this one, we'll just keep them all the same radius. And then we'll put these goals into the entwine. We'll put all of this into the goal objects. And I'm actually going to hide everything so far except for the surface. And then I'm going to get a bang component, explode tree. And the top one is going to be our points. That's what we're showing. Let's get a clean tree. This will just get rid of our nulls. So these are the points that we're interested in. Let's get a circle component. Put this into our radius, or our display hidden. So let's see what happens as we increase the radius a little bit. These are spread more and more uniformly across the surface. So there is a hexagon pattern starting to emerge here. Obviously this isn't perfect, but let's see if we can identify that hexagon pattern. I'm going to get a curve component, and let's just grab our original curve and put it in there. And then this continuity, this is going to get all the points. And these are going to be our perimeter points. We're going to merge these points together with all of our points that came out of the zombie solver here, all of these points. So I'm going to get a merge component. Let's flatten these as they come in, just to make sure that they're all in the same list and treated the same way. Let's type in Delineate. AU. So we want this one that says Delineate Edge. I should step in right now and say the way that I did it the first time we recorded this was I took one extra step, and so I'll just jump in to fix that. I said just now you should grab the Delineate Edges component, but you shouldn't. You should grab Delineate Mesh. This is much easier, so plug that in. And actually, there's no real reason to merge together the points from the curve, so we can delete all this too. So let's make this quite a bit shorter. So out of our clean mesh component, we're going to plug the points right into the Delineate Mesh component, and then from Delineate Mesh, we're going to get something called dual graph, Weaverbird's dual graph. And so what this is doing, I'm going to hide this and just get a mesh component so we can see these two side by side. So what the dual graph does is it makes a point at the center of each face of a mesh and then connects the lines. And so we get something like a new mesh. But this isn't actually a mesh, these are just polylines. And if you don't have Weaverbird, you can do something very similar with the Voronoi component. We'll plug these points into Voronoi, And we can also get a boundary. Let's go over here and get our initial curve. And I'll plug that in there and go to wire display hidden. Then let's bring this over here. Don't worry about all the extra stuff on the canvas. We'll get to that in a minute. And so let's hide all of this. You can see that the Voronoi, this is Voronoi right here, and the dual graph are very similar. These are related and appear very similar in some cases. If these points were perfectly spaced, they'd be exactly the same. But the point is, we can see a hexagon pattern starting to appear. Okay, now I'll put you back into the original recording. So let's go back and make this one again, and let's clear all of these points and just start over with a set of new points. So I'm going to right click and say set multiple points. And then let's increase the radius. We can see again that hexagon pattern starting to appear. Anyway, that's fine. We can do a much cleaner version of this pretty easily. So let's disable this component and we can hide all of this. Again, let's get an empty curve component and we'll reference a different curve. I'm just going to type CI because that's my shortcut for interpolate curve. So for you, if you just type interp curve into the Rhino window, you can start making whatever kind of curve you want. I'll right click here and say set one curve. Let's turn this into a surface. Now let's get a try remesh. So under the mesh tab, under triangulation, there's a component called try remesh, and this is great because this basically just divides up a surface for us. Here we can see that all of these points, all of the vertices of this mesh are pretty evenly distributed, and the edges have made what are very near to equilateral triangles. So let's visualize the circle packing from this. Imagine that we want circles that are all exactly touching each other at their tangent points. We want to cover a surface with maybe bumps that are all just barely touching each other. This equilateral mesh is a great place to start. And again, we're going to use Kangaroo because in computational design, there are a lot of advantages to just simulating how the world actually works, simulating physics, and Kangaroo can help us do that. So again, I'm going to get a show component. Let's show this mesh. I'm going to get an entwine, put this up here, and let's type in tangent in circles, this one right here. This takes in a mesh. That's this component right here under the goals mesh tab. That can be our goal that goes into our second branch here. And again, let's get a zombie solver. Put these in. Let's hide all of this. I'm going to internalize this and delete the line. Now we can change the size of these triangles by changing the length of the edges to target. So I'm going to get a slider between 1.000 and like 8. That's way too big, so let's make the max 1 and the minimum 0.25. Okay, that's good. Then again, let's get a bang. We'll take the first branch and clean. Next, let's go up here and get the tangent circles. That's under the mesh tab, tangent circles. Let's hide all of this. And let's get two curve components. So the first one, this is going to be our hexagons, or in some case, pentagons. And some of these don't even have 5 sides, but a lot of them are going to be hexagons. You can think of this as kind of like the Voronoi pattern surrounding our output points. If the output points are the vertices here, more specifically, this is the dual graph. Every face from this mesh is now treated as a vertex, so the center point from each face now becomes a vertex. And if we go in here, we would put like a vertex here, and draw a line between them. And so that gives us something that looks like this. And this isn't actually a mesh, this is just a list of polylines, and these are the circles. So this is a really nice and easy way to pack circles on a flat surface. In the next video, we'll pack circles on a sphere. Thanks so much for watching. See you there.